Hello everyone, it's a pleasure meeting you again in my mathematics class. Today, let me discuss Erlang distribution, which is also a continuous distribution. We say that a random variable x follows the Erlang distribution f of fx. This is Erlang distribution x lambda k, where lambda k are all parameters. If PDF is given by fx of x is equal to lambda to the power of k minus 1 factorial x to the power of k minus 1 minus lambda x greater than 0, and this lambda is greater than 0 and k belongs to z plus, that it takes all positive integers here. So this is we say that, so this is a continuous random variable and this is the probability density function of Erlang distribution. Now let me work out the mean and variance of the Erlang distribution. See, we know that a of x is equal to, it is 0 to infinity because the distribution is defined in 0 to infinity. It is x into fx into dx, where this fx is nothing but Erlang distribution functions PDF. So this is equal to, I will take this, see, it is lambda to the power of k minus 1 factorial into the integral x into x to the power of k minus 1 e to the power of lambda x into dx. So this is nothing but lambda to the power of k minus 1 factorial 0 to infinity x to the power of k into e to the power of minus lambda x into dx. Now you see that let lambda x is equal to u. This implies x is equal to x by lambda. X tending to 0 implies u tends to 0, and x tending to infinity implies u tends to infinity. X to the power of k is equal to u to the power of k divided by left k, and dx is equal to du by k, du by lambda. So substituting all these things, see, we go for change of variables. Now what happens is that, so this e of x, it becomes lambda to the power of k divided by k minus 1 factorial into, so this is nothing but 0 to infinity, x to the power of k is u to the power of k divided by lambda to the power of k into e to the power of minus u into dx is du by lambda. So this is nothing but, see, this is, see, the lambda to the power of k, lambda to the power of k will go off, leaving you with 0 to 1 by lambda, 0 to infinity, then it is u to the power of k into e to the power of minus u into du. So this is what we get. So this is divided by, it is a k minus 1, it is k minus 1 factorial into lambda into k minus 1 factorial. Now this is a gamma function. This is a gamma function. So this is nothing but, so this is equal to, it is, so this is a gamma function. So you get this to be your, so you can write this as 1 by lambda into k minus 1 factorial into 0 to infinity of u to the power of k plus 1 minus 1 and e to the power of minus u into d. So this is nothing but what? It is, if it is n minus 1, it is n factor gamma of n. This is k plus 1 gamma of n. So this is, so gamma plus 1 factorial is nothing but, it is k plus 1. It is a k factorial. It is k factorial. Gamma of k plus 1 is k factorial divided by lambda into k minus 1 factorial. That is k minus 1 factorial into k divided by lambda into k minus 1 factorial. So these two will go of give me what? Because we know that it is a gamma of, see, gamma of n is n minus 1 factorial and gamma of n plus 1 is n factorial. So these two things we must know. So how do we get this? So we have not done anything. I have applied the definition of the mean e of x is equal to x into f of x into this. After that, I have done some manipulations here, taking this lambda x is equal to u. I have gone for the change of variables, and here I have used that, I have used the idea that this is a gamma function, and the gamma function is nothing but it is gamma of k plus 1, but gamma of k plus 1 is nothing but factorial k, and therefore on simplification we get the value to be e of k by lambda, that is e of x is equal to k by lambda. So this is what we get. So this is the mean of the distribution x, which follows of the distribution x, which is a Erlang distribution. Now let me find out what is sigma, our variance. To find variance, see, to find, see, we know that variance is equal to e of x squared minus e of x whole square. Now e of x squared is equal to, it is nothing but lambda to the power of k divided by k minus 1 factorial into 0 to infinity. If you put x squared, it is nothing but it is x to the power of k plus 1 into e to the power of minus lambda x into dx. Now if we go for the same substitution here, you will find that lambda to the power of k minus 1 factorial into 0 to infinity. See, x to the power of k plus 1, see, x to the power of k is this is u to the power of k plus 1 divided by lambda to the power of k plus 1. Here x to the power of k plus 1 into e to the power of minus u into du by lambda. So this is equal to, you see, this is k, lambda to the power of k, lambda to the power of k will give you, it is 1 by lambda squared a k minus 1 factorial 0 to infinity u to the power of, this is nothing but you can write this as k plus 2 minus 1 into e to the power of minus u into du. But this is nothing but your gamma function. So this gamma function is nothing but what? It is 1 by lambda square k minus 1 factorial into, so this is nothing but your k plus 2 gamma of k plus 2. So this is nothing but gamma of k plus 2 is nothing but it is k plus 1 factorial divided by lambda squared into k minus 1 factorial. This is equal to k minus 1 factorial into k plus 1 divided by lambda squared k minus 1 factorial. So this is equal to, here it is k into k plus 1 divided by lambda squared. So this is what we get. So e of x squared is equal to so much. Therefore, variance of x is equal to sigma of x squared is equal to, it is k into k plus 1 divided by x squared minus k squared by s squared. That is k squared by lambda squared plus k by lambda squared minus k squared by lambda squared. So these two will go in give k by lambda squared. So this is here again I have not done anything. Here e of x squared I am finding. E of x squared is x squared into this probability density function. So x squared means we will get k to the power of a k. In lambda to the x to the power of k plus 1. Then I have gone for the same change of variables and I substitute in this place. This is a gamma function which is equal to k plus 2 of gamma. So k plus 2 of gamma is nothing but our k plus 1 factorial. Then on simplification I get k into k plus 1 by lambda square. Now we know that sigma of x squared is equal to, which is nothing but the variance. This is equal to e of x squared whose value has been got. That is k into k plus 1 divided by lambda squared minus e of x. We have already found k by lambda. So k squared by lambda squared. On simplification we get this. Therefore our sigma of x squared is equal to k by lambda squared. So this is how we calculate the, what we find the mean and variance of the Erlang distribution. Now let me come to the problem. What is the problem here? It is given. We are asked to find, that is, a call center models the time until a technician finishes servicing a customer asset. So you see that the finishing of a call center models the time until a technician finishes servicing a customer as an Erlang distribution with k is equal to 3 and lambda is equal to 3. Lambda is equal to, it is lambda is equal to 2. This is not 3, it is lambda is equal to 2. It is not 3, it is lambda is equal to 2. This lambda is equal to 2. Now find the probability that the service time lasts more than. So you see that the service time has been, the service time of a technician is able to finish his service and the service time follows the Erlang distribution. See, there is a call center where the technicians are working and the service time of the technician is found to be a Erlang distribution with k is equal to 3 and lambda is equal to 2. Now we are going to, the question that is asked is, what is the probability that the service time of a technician does not last more than 1.5 units of time, because here it is not mentioned whether the servicing time is in minutes or in hours, something like that. It is just units of time. So there is things come for servicing and in certain arrival time, but the servicing time is found to follow Erlang distribution with k is equal to 3 and lambda is equal to 2. We are asked to find the probability that the service time for a technician is not more than 1.5 units of time. What is the probability that the service time of a technician for servicing a thing does not exceed, is not more than 1.5 units of time? That is the question. Okay. Now, here is that this is a very simple problem that you can easily approach. We know that, see I write it here. See, we know that P of x less than or equal to x is equal to, it is 0 to x fx into dx. This is, so here you see that here x is equal to 1.5 and x follows Erlang distribution with x and it is k is equal to 3, lambda is equal to 2. Therefore, what is therefore? Therefore, P of x less than or equal to, it is 1.5 units of time will be equal to 0 to 1.5. It is lambda to the power of k. What is lambda here? Lambda is equal to 2, k is equal to 3. So lambda is equal to 2 means it is 2 to the power of 3 divided by 3 minus 1, 2 factorial is simply 2 into x to the power of k is 3 means 2 and e to the power of minus 2x into dx. So this will be equal to 4 into, I will straight away write this. This is nothing but if you take this 2 outside, I will use Bernoulli's method of integration. So this is x square e to the power of minus 2x divided by minus 2. This must be 0 to 1.5 minus, differentiate this 2x divided by minus 2 into integration of this is e to the power of minus 2x minus 2 and this is 0 to 1.5 in plus, differentiate this 2x, it is 2 divided by minus 2 and this comes 1 by minus 2 into integrate this e to the power of 2x by minus 2 and this must be raised to the limits of 1.5. So I have not done anything, simply I apply the Bernoulli's method of integration, and if you simplify this, that is you put 1.5 for 0, this will be 0. Second limit will be 0, second limit will be 0, but second limit will exist here. Because here no x comes, so e to the power of 0 is 1. So first limit we put like this, say 1.5. So this is nothing but what? It is, so if you apply, see put x is equal to 1.5 here, for second limit will be 0. Put x is equal to 1.5 here, second limit will be 0. But here you will find that you can put, you have to apply both the first limit and the second limit. If you simplify this, it will be 0.6768. That is P probability of x less than or equal to 1.5 is equal to 0.6768. That is the probability, there is, see, there is a probability of probability of 67.68%. There is a probability of, there is the probability of finishing the service by the technician that is the probability of finishing the service by the technician, by a technician, is 0.6768 or 67.68% chances. This one or 67.6658 chances. So this is all about so here I have not done anything. Here it is, we know that p of x less than or equal to x is equal to 0 to x of f of x dx. But here in this case, f of x is nothing but our Erlang distribution. The values of lambda and k are given. So substituting the values, and I use the Bernoulli's method of integration. On simplification of this, we will get 0.6768, which is nothing but there is a problem of 0.6768 chances that a technician will finish it within 1.5. See, by technician pointing to finish to finish not taking finish within, see, to finish within 1.5 units of time. See here, the probability of finishing the service by a technician is 0.6768 to finish, 68 chance to finish within 1.5 units of time. That is 67.68% chances are there that the technician will finish, will not exceed 1.5 units of time. So this is all about the problem involving this one. Okay, I will deal with more difficult problems in coming days. Thank you.